Okay, so I'm just doing a review on some analysis, and in this case we're doing just proof by induction, and I just thought I would go over it for the sake of review and also if it helps anyone. So this is just from the textbook, and I'm going to go through a couple examples that I think is worth going through. So I'm going to start with example 1.33, which wants us to prove that the sum k equals 1 to n of k is equal to n times n plus 1 over 2. So by doing induction, the first thing you would do, step 1, is let's say for n equals 1, right? So on the left-hand side, obviously, you would just have 1 equal to 1 plus 1, or 1 times 1 plus 1 over 2, which is 1 equals 1. So for the first case, it does work. Okay? So now what we're going to do is we're going to say this summation, which is 1, should be k, 1 plus 2 plus 3 plus ... n is equal to n times n plus 1 over 2. So we're just restating the proof, what we're trying to prove. Okay, so this is our statement, and we showed that in the first case it works. We assume that this is true, and now what we want to do is show that for the case k plus 1, it's also true. So 1 plus 2 plus 3 plus ... plus k plus 1 equals, so now you would have k plus 1 instead of n, and then you would have k plus 1, so k plus 2 over 2. Okay? Well, if we rewrite this slightly different, you could see that this is equivalent to 1 plus 2 plus 3 plus ... And if we think about the term before k plus 1, it's just going to be k plus k plus 1. So we're just adding this sum. We add to k, and then we're going to add another term, the next term, k plus 1, which is equal to all this stuff. And this is the part that we take for being true as above, right? So we know that is just k times k plus 1 over 2 plus k plus 1, the additional bit that we have. Okay? So this part is that from above. Okay? And if we want to here, we can see that this if we want to go ahead and write it under one fraction, that's just k plus 1, k plus 2 over 2, right? So we would just multiply this by 2 over 2 to get a common denominator, and you would get k times k plus 1 plus 2k plus 2 over 2, k squared plus 3k plus 2 over 2, and then that can be factored into this, right? The numerator can. And this is equal to this. So we were able to use induction to show that to be true. Okay? So now we can say that's true for whatever case it is that we're interested in, not necessarily the k plus 1. So the next example, 1.3.4, it tells us to prove this. X to the power n plus 1 minus 1 equals x minus 1 times x to the n plus x to the n minus 1 plus ... plus x plus 1. So that's what we need to show, and just like in the last step, the first step is to see what happens. This is your statement. Right, this is your statement. And what happens when n equals 1. So this is just the one case that we need to prove to begin with. And when you do that, you'll get x squared minus 1 equals x minus 1. And then you'll have x to the power of 1, right, plus 1, because you'll have x to the 0. And obviously this is a difference of squares, so you can see that that's true. So for the n equals 1 case, it does hold. Okay, so now for a general case, we'll say x to the k plus 1 minus 1 equals x minus 1 times x to the power k plus x to the power k minus 1 plus ... plus k, or plus x plus 1. So that's, we'll take this as being true. Just assume that this is true. Okay. And now we want to prove the case for k plus 1. So you'll have x to the, we'll basically replace this k with k plus 1. So this becomes k plus 2 minus 1 equals x minus 1 times x to the power k plus 1 plus x to the power k plus ... plus x plus 1. So this is what really the bulk of our work is now that we have to prove. Okay? Okay, so let's see. How should we go about this? Well, we could start by rewriting x to the power k plus 2 minus 1. This is equivalent to x times x to the power k plus 1 minus 1 plus x minus 1. Because if you were to distribute this, right, that's going to be x to the k plus 2 minus x plus x minus 1. And we get our original statement. But we're rewriting it in a term that includes this factor of x to the power k plus 1, since that's what we know about. That's what we're assuming to be true, right? This, I don't know why my pins are so small right now. This we assume to be true, and this is kind of where we're at. So now we can actually substitute that in, which is what we want to do. And when you do that, you'll have your x minus 1. Let's factor out, let's do this, x times x minus 1. So this x is coming from here. You'll have your x minus 1. And then you'll have x to the power k plus 1. I'm sorry, just k plus x to the power k minus 1. Yeah. plus dot 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 plus x plus 1. Okay. And then we still have plus x minus 1 from right here. Okay, so that just comes down. All right. So now what should we do? Well, we can pull out a factor of x to get rid of this x in the front. So if we pull an x out from this guy, 1 over x, that'll make that x go away, right? And we'll be left with x to the power k plus 1 because we factored an x out, so that's going to increase our exponent, plus x to the power k. I hope I'm saying this correctly. I know I'm writing it down correctly, but you know how it can be, plus x squared plus x, and then we still have our plus x minus 1. Okay. So that's from factoring out a 1 over x at this blue part to cancel this x, and then we get this where all your exponents are raised essentially to a power. And now you can see this common factor of x minus 1 on both sides. That can be factored out, and you'll still have this stuff here, plus dot 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 plus x squared plus x. Okay. And yes, I think we're good there. And that'll be equal to whatever we had before, which was x to the power k plus 2 minus 1. Let me double check this. Oh, yes, plus 1, because we're factoring that out. I forgot that. Okay. Plus 1. Of course, there should be a plus 1 because we factored out from there as well. Okay, so that's good, though. So we proved that. Okay. Now let's see. What was the next part I wanted to talk about? Believe I wanted to, I don't know if I should prove. I mean, they kind of do it there with 1.36. Maybe they skip some steps, so it's worth doing. Yeah, I'll do 1.36. Okay, so with 1.36, we have n choose k plus n choose k minus 1 is n plus 1 choose k. And n choose k, just to have handy, is n factorial over k factorial and minus k factorial. So this is just a shorthand of writing it because it comes up quite a bit. Okay. All right. So if we want to, I guess, start by rewriting this, just following our equation, that's n factorial, k factorial, and minus k factorial plus n factorial over k minus 1 factorial times n minus k plus 1 factorial, right? So just using the definition and plugging in, there we are. So now, I guess this part's a little weird. I'm going to multiply, let me move this over maybe. I'm going to multiply this by n plus 1 minus k over n plus 1 minus k. That's just 1. I'm allowed to multiply by just 1, right? And I'm going to multiply this by k over k. Again, just 1, so that's fine. But why are we multiplying that by that? That seems a little bit random. Well, it actually cleans up quite nicely. So I'm just going to write this down. And I'll show you, and it's kind of cool. And then you have okay, so there's that first part. And then multiplying the k on the other side. Okay. So this, you have n minus k plus 1 and then n minus k factorial. So this whole thing is n minus k plus 1 factorial, right? Because you're multiplying basically n minus k plus 1, and then the factorial is all the previous factors that are dropped by 1. So that's just that. And then over here, you can maybe see it's the same thing. This is just k factorial, right? Just written maybe a little bit strange. Okay, so then you get n factorial n plus 1 minus k over k factorial n plus 1 minus k factorial plus n factorial k over k factorial n plus 1 minus k factorial. And we can factor out from both of these an n factorial in the numerator, a k factorial in the denominator, and an n plus 1 minus k factorial also in the denominator. Well, in the first term, you're just going to be left with n plus 1 minus k from this bit. And then on the other side, there's just a plus k. So the k's drop, right? And you'll just have n plus 1. So we have n factorial times n plus 1. So just like the logic above, this is n plus 1 factorial. So n plus 1 factorial over k factorial n plus 1 minus k factorial. And if you remember our little equation, our numerator now is n plus 1, and in the bottom it's still k. So n plus 1 choose k. So as you can see, we did prove this all right. I think that's all I'm going to do for now, but if people want more videos like this, I can do that. Just let me know.